You know, for decades, fusion energy has felt like this ultimate dream, harnessing the power of the stars right here on Earth. And the promise? It's just incredible. We're talking about abundant, clean energy with pretty much no long-term radioactive waste and zero chance of a meltdown. It's really the holy grail of power. But for just as long, it's been the subject of a kind of running joke.
And yeah, for as long as that promise has been around, there's been this joke in the scientific community. Whenever anyone would ask when fusion power would finally be here, the answer was always the same. Oh, it's 30 years away, and it always will be. It was just a clever, kind of cynical way of saying, yeah, don't hold your breath.
But here's the thing. Something has fundamentally changed. That old joke, it just doesn't land anymore because, well, it's not true. The whole era of fusion being some perpetual fantasy, that's over. We have entered a completely new phase.
So what changed? Well, for one, money started talking. A lot of money. We're now seeing this massive wave of private capital, with total investment blowing past $9.8 billion. And this isn't just government research grants anymore. We're talking tech giants like Microsoft and Google, and investors like Jeff Bezos and Sam Altman, all placing these huge bets that fusion is about to become a commercial reality.
And all that confidence? It's really built on this. Back in 2022, scientists at the U.S. National Ignition Facility hit a milestone that changed everything. For the very first time in history, they achieved what's called ignition. They actually got more energy out of a fusion reaction than the laser energy they had to put in to get it started. I mean, that's the whole ballgame. That was the moment the entire conversation shifted from, is fusion even possible, to, okay, how do we actually build this thing? But going from a scientific proof of concept in a lab to an actual power plant on the grid, that's a whole different story. It means facing two very different and very difficult sets of challenges. It's one thing to prove the dream is possible. It's another thing entirely to run the gauntlet of reality.
And you can really break it down into these two paths we have to conquer at the same time. On one side, you've got the pure technology risk, right? That's the immense engineering challenge of, can we physically build and sustain a miniature star? Then on the other side, you have the systemic risk. This is all the real-world stuff, the regulations, the supply chains, the politics, all the things that can stop even the most amazing technology dead in its tracks.
All right, first up, let's dive into that technology risk. The central challenge here is, and I'm not exaggerating, literally bottling a star.
I mean, just take a look at this. This is not some sci-fi movie set. This is the inside of a real fusion machine. The sheer engineering complexity is staggering. You're trying to contain plasma that is hotter than the sun, and to do that, you need some of the most advanced technology humanity has ever come up with.
So the materials inside these reactors have to survive what you could only call a gauntlet of abuse. They have to withstand temperatures over 100 million degrees. At the same time, they need to survive a constant, intense bombardment of high-energy neutrons, which can just shred most materials over time. And they have to do all of this while managing a super complex fuel cycle without the parts facing the plasma just falling apart.
And about that fuel cycle, it's a really big one. Most fusion designs rely on a fuel called tritium, which is incredibly rare on Earth. So the only way to make this whole thing work is for the reactor to actually breed its own fuel. The idea is that neutrons from the reaction hit these special lithium blankets, and that creates more tritium. It's an absolutely brilliant concept, but here's the kicker. It has never, ever been proven to work at the scale you'd need for a commercial power plant. And without it, the whole system just doesn't work.
Okay, so let's just say we solve all of those immense engineering problems. Even if we do all that, we're only halfway there because next up we have to navigate this maze of systemic risks.
And believe me, this second gauntlet is just as tough. For starters, the supply chains for critical parts like high-temperature superconductors, they just don't exist at scale yet. There's no clear, unified set of rules for how you even license and regulate a fusion power plant. We're facing a growing shortage of people with the specialized skills to build and run them. And on top of all that, rising geopolitical tensions could threaten both global collaboration and access to key materials. But the good news is, people are already working on solutions. In the US, for instance, experts have laid out a pretty clear roadmap to cut through all that red tape. The ideas are really straightforward. Create an efficient licensing process that works for mass-produced reactor designs, fast-track the environmental reviews, and make it way easier to connect to the grid, especially for huge power consumers like data centers. This is how you turn an abstract problem into a concrete plan.
But at the end of the day, for any new energy source, it all boils down to one simple question.
Can it compete on price? So, what's the real cost of fusion?
And this right here is the prize. This is why everyone is so excited. New research projects that once the technology is all grown up, fusion could deliver power for as low as $25 per megawatt hour. Now, to put that in perspective, that is half the cost of onshore wind. And get this, a staggering 4 times cheaper than traditional nuclear fission. That's a total game changer.
But, and you knew there was a but coming, here's the catch. That amazing $25 figure, that's for a mature industry way down the road. The very first-of-their-kind plants are going to be incredibly expensive. We're talking an upfront capital cost of anywhere from $4,000 to $12,000 per kilowatt. That is a massive investment hurdle to clear.
Which leads us to the billion-dollar question. Literally, how do you bridge that gap? How do you get from a multi-billion-dollar prototype that costs a fortune to that ultra-cheap $25 power? Well, the answer really lies in technological learning, doing it over and over, and just scaling up manufacturing.
And this is where it all comes together. We're in the final leg of this story now. The intense, high-stakes, global race to actually get fusion power onto the grid.
You know, for a field that's been 30 years away forever, the timeline is now accelerating like crazy. After that 2022 ignition breakthrough, the next huge milestone is right around the corner, 2028. That's when Helion is scheduled to deliver the world's first fusion power to Microsoft. From there, the target is to get the first commercial plants hooked up to the grid in the early 2030s, and there's a pretty broad consensus that the first generation of plants will be up and running by 2035.
So here we are, standing right on the edge of what could be a totally new energy era, and it really leaves us with this one big final question. The battle against the laws of physics. That one is nearly won, but a second battle, the one against our own complex systems of regulation, supply chains, and politics, that one's just beginning. So which of these two races will ultimately prove harder to win?